Again, he changed the temperature at 13.1 degree. At 13.1 degree, he observed that as we increase the volume, this critical volume is the volume which is occupied by the 1 mole of gas at a critical temperature and a critical volume. So, the number of particles will get evaporated should be equal to the number of particles which is get condensed. That is known as equilibrium state. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in this session, we are going to discuss with another unit called as States of Matter. So already we are dealing with this unit. Under that, we have studied about the kinetic theory of gases, and also we have understood the behavior of the real gases and the deviations of the real gases, and also we have learnt about the causes for the deviation in the real gases and the differences between the real gas as well as with the ideal gas, and also we learnt about the Van der Waals equation and the compressibility factor. Today, let us move on to the next topic of this unit about the liquefaction of the gases. And also we are going to understand about the liquid state. In that, we are going to understand with the vapor pressure, surface tension along with the boiling point. So firstly, I'll go for the liquefaction of gases. Here, before going to understand what actually the liquefaction of gases, first we will see the Andrews curve for the carbon dioxide. So the Thomas Andrew, he obtained the critical isotherm of carbon dioxide. This is an isotherm of carbon dioxide and it was first discovered by Thomas Andrew. So in the x-axis, he taken out the volume and in the y-axis, he plot the pressure. So at the beginning, what does he observed in the sense, as we increase the pressure and the volume, the gases will behave differently. And one of the most important thing is, he observed these changes by taking with the different temperature. At a particular temperature, if you raise the pressure and the volume, how does the carbon dioxide will behave? That was first discovered by or first observed by Thomas Andrew, and this curve, which is also known as Thomas Andrew curve of CO2, that is carbon dioxide. Now let us understand what all the observation he has made by plotting the pressure versus volume. Okay. So in the x-axis, he put the volume and in the y-axis, he considered the pressure. So firstly, he took the carbon dioxide as one of the gases as at a particular temperature called as 50 degree. At a particular temperature called as 50 degree, he observed that the gases will behave ideally and it just gives a curve. At a temperature 50 degree. Okay. As you increase the temperature, the gases will be comes down and the volume will be very less. The same thing he considered the carbon dioxide by changing the temperature at 31.1 degree Celsius. At 31.1 degree Celsius, he observed that the gases will be again, it will be increase and it will be decrease. Again, it will be increase and decrease, or you can see from here to here. So, due to these changes in the temperature, he has observed that these gases, that is the carbon dioxide gases, they behave ideally. Again, he changed the temperature from 31.1 degree Celsius to 30.98 degree Celsius. He observed that when he increased the volume, the gases will be goes up at a particular point, at a particular point called as E, the entire gases, that is a CO2, is completely converted into liquid, where the carbon dioxide is converted into liquid. At a particular temperature, that is at 30.98. At this temperature, what happened when he is increasing the volume? At a particular point, the entire gas is converted into liquid. This is known as critical temperature. Again, he increased the pressure and this gas will give a straight line. By changing the temperature, again he observed that this gas, at a temperature 21.5 degree. As we increase the volume of this gases, it will give a straight line. Again, at a particular point from the C to D, almost all the gas and gas molecules will be started converting into liquid. Here, the gas molecule is converted into liquid and this is a phase where the gas molecules are completely equal to the liquid molecule, where the gas molecules will be started converted into liquid. Understood? So, this is a space where this is a temperature at which the gas molecules are started converting into liquid. After this, if you increase the pressure, again the entire gases will be converted into liquid. But there is only certain temperature at which the entire gases will behave like both the gases and the liquids, where the gas molecules will be started converting into liquid. Again, he changed the temperature at 13.1 degree. At 13.1 degree, he observed that as we increase the volume, the entire horizontal line will be increased. There is a longer time for the conversion of gaseous state into liquid state, and this phase where the gas molecules are completely equal to the liquid molecules, again when you increase the pressure, the entire gas will be converted into liquid. This observation was made by the Andrew, hence it is also known as Andrew isotherm of carbon dioxide. By changing the temperature, he observed that at a particular temperature, at a particular volume, at a particular pressure, the entire gases is converted into liquid, or the entire gases is started converting into liquid, and there is a large difference in conversion of gases into liquids. This observation was made by the Thomas Andrew. At a higher temperature, say about more than 30.9 degrees, say about 50 degree, the isotherm shows the ideal behavior. This is the ideal behavior of carbon dioxide. So, hope you all understood that how he explained this graph by taking carbon dioxide. So, if you ask me that whether it is too important to learn this entire graph, no, it is not very necessary to learn the graph. Only thing is here the three constants will become, that is a critical temperature, critical pressure and a critical volume. The three definition you must learn because that can be asked for the 1 mark. After this, here he explained that the liquid and the gases that can be coexist only with the certain region which is given by the shaded region. Here you can see that the gas and the liquid, they will coexist with each other. Is it right? Especially at the temperature called as 21.5 degree, the gas and the liquids, they are coexist in a particular distance. But as you make the temperature less, that is at 13.1 degree, what will happen? The distances between or the coexistence of the liquid and the gases will be more. And as the temperature and the pressure is increased, the shaded region will become more narrow and finally it reaches to 0 and it is known as critical point. And the values of pressure, volume and temperature at this point are also known as critical constant. That is critical temperature, critical pressure and the critical volume. The isotherm that passes through the critical point are also known as critical isotherm. The isotherm is the graph at a particular temperature. They are known as the isotherm which passes the critical point. They are known as critical isotherm. Beyond this critical isotherm, the gases and the liquids, they become distinguishable and there is only a single fluid phase. They are known as supercritical liquid. Here you can see that at a temperature of 30.98, the entire gases is converted into liquid. After when you increase the pressure, the entire gases is completely become liquid. Hence it is known as supercritical liquids. It is also known as supercritical liquids. Okay. And also here you can see that at a temperature of 21.5, there is a coexistence of the liquid and the gases. Is it right? After that, when you increase the pressure, the gas molecule which is converted into liquid and it will form a supercritical liquids. It forms a supercritical liquid and finally it approaches to zero. This is how he explained the entire graphs by taking the carbon dioxide as one of the gas to explain this isotherm. Next we'll see what is this critical temperature, critical pressure and a critical volume. So these three are also known as critical constant. The critical temperature is nothing but a temperature above which the gas cannot be liquefied by applying the pressure. It is a temperature above which if you apply the pressure also, the gas cannot be get liquefied. Here you can see from this graph at a temperature of 50 degree and a temperature of 31.1 degree. When you are applying the more temperature, even though the gas molecule is not converted into liquid. Hence it is known as critical temperature. Then what is critical pressure? It is a minimum pressure required to cause the liquefaction at critical temperature. It is a minimum pressure required to liquefy the gases into liquid phase. When you can see the critical pressure, especially in this point, where you can see that the temperature around 30.98. There is a small differences with the 31.1 degree to the 30.98. Is it right? This is a minimum pressure which is required. This is a minimum pressure that is a 73 atmosphere which is required to liquefy or to convert the gases into liquid at a critical temperature which is known as critical pressure. Remember, it is nothing but a minimum pressure which is required to convert the gas into liquid at a critical temperature. Next, critical volume is the volume which is occupied by the 1 mole of gas at a critical temperature and a critical volume. It is a volume which is occupied by the 1 mole of gas at a critical temperature and a critical pressure. Then lastly, we have learned about supercritical fluid. It is a dense fluid which is obtained by compressing the gas above the critical temperature called as supercritical fluid. So where you are condensing the entire gas into liquid state. Hence it is known as supercritical fluids. Hope you all understood with the three different critical constant. Remember, it is also very important for the examination point of view. For most of the time, they have asked what is critical temperature, what is critical pressure and a critical volume. Okay. Hope you all understood with the three definition. Next, we'll go with the liquid state. Till now, whatever we have learned, it is only about the gases. Now, we'll shift on to the next part to learn about the liquids. Already we all know that the liquids, they have a definite volume, not a shape. It always takes the shape of the container and they acquire the shape of the container. In the liquid, we have understood that the molecules have a translatory motions and that is why they have fluidity nature. Because of this translatory motions of the particles in the liquid, they have become fluidity. They are fluid in nature. They can easily flow from one container to another container. And it takes the shape of the container. The intermolecular forces in the liquid is stronger than that of the gases. The force of attraction, between the liquids are almost stronger when it is compared with the gases. Okay. Then the liquid molecules are become very closer to each other and they have a less space between the molecule. And usually, this particles of the liquids, usually they are very closer to each other. So, they are very closer to each other. They will be like this. And also, when compared to solid, the particles are somewhat freely arranged. And there is to understand this concept, the first we will take on out with the example of any liquids. Okay. So, especially with the volatile liquids, if you consider, imagine this is a liquid which is in the liquid phase. So, I have taken the liquid in the closed container. What will happen? As I told that these are the liquids which is volatile in nature, which means to say that it can easily evaporate. Okay. So, when you take the liquid in a closed container, what will happen? The particles or the molecules which is present in the liquid state, after some time, it will be start evaporating towards the vapor phase. It will be started evaporating to the vapor phase. After some time, when the molecules will be goes to the vapor phase, again it will be condensed back to the liquid state. During that condensation, it will exert some pressure on the surface of the liquids. On the surface of the liquid, these particles, they exert, or the molecules of the gases or the molecules of the liquids, it will exert some pressure that is said to be vapor pressure. So, what is the vapor pressure? Vapor pressure of a liquid is a pressure exerted by the vapor when the liquid and a vapor are in the dynamic equilibrium. So, what is the dynamic equilibrium state in the sense? When the molecules of the liquid goes to the vapor phase, we know that it never stays longer time in the vapor state. Again, it will be comes down. So, the number of particles will get evaporated should be equal to the number of particles which is get condensed. That is known as equilibrium state. Okay. So, during that state, what will happen? These particles, when they are moving down or when they condensed back, it will exert some pressure on the surface of the liquid. That is said to be, vapor pressure, and it is exerted by the vapors of the liquid on the surface of the liquid. Suppose if I add any solute to this liquid, what will happen? Obviously, the solid particles will be goes and settle at the down and also on the surface of the liquid. In such situations, this vapor pressure will be decreased. The vapor pressure will be decreased. Why vapor pressure will be decreased when you add the solute to the solvent? Because the solid particles will be goes and settle at the bottom as well as on the surface of the water, and it does not allow the liquid to get evaporated. If there is no evaporation in the sense, obviously there will be a no vapor pressure exerted by the vapors of the liquid. So, this is how when you add the solute to the solvent, vapor pressure is also get decreased. Hope you all understood with this concept. Next, we'll see with the boiling point. So, let us understand what is the boiling point first. It is the temperature at which vapor pressure of the liquid is equal to the atmospheric pressure. It is a temperature at which vapor pressure is equal to the atmospheric pressure. For example, if you consider any liquids, we all know that water will be boiled. Is it right? If you taken out in the closed container, it will get evaporated. Is it right? Suppose if you are boiling the water, what will happen? The water molecules will be start boiling. As a result of this, some of the molecules will be goes to the vapor phase. And also it comes back to the, and once it is cooled, again it comes back to the, again it will be condensed and come back to the liquid state. So during this process, what will happen? The temperature at which the vapor pressure of the liquid will be equal to the atmospheric temperature. Atmospheric temperature means surrounding temperature. At a particular temperature, when you go on heating, the vapor pressure will become equal to atmospheric pressure. The entire vapor pressure of that liquid will be equal to the atmospheric temperature, that is said to be boiling point. Remember, boiling point, it is very simple. Suppose when you heat any liquid, we all know that some of the particles will go to the vapor phase, where when it goes to the vapor phase, it will create a vapors. When again it combines to the liquid phase, it will exert some pressure, that is said to be vapor pressure. At a particular point or the particular temperature, we can say, at a particular temperature, especially for the water at 100 degree, we know that it boils at 100 degree, is it right? So at a particular temperature, the vapor pressure of the water should be equal to the vapor pressure of the atmospheric pressure. Okay, that is said to be the boiling point. And also, if the atmospheric pressure is equal to 1 atmosphere, then the boiling point is said to be normal boiling point. Suppose if the pressure is 1 bar, then the boiling point is said to be standard boiling point. If the pressure is said to be 1 atmosphere, then we say it is a normal boiling point. If the pressure is said to be 1 bar, then we say it is a standard boiling point. Standard boiling point. The standard boiling point of the liquid is slightly lower than that of the normal boiling point, because the 1 bar pressure is slightly lesser than that of the 1 atmospheric pressure. The normal boiling point of the water is usually 100 degree, and the standard boiling point of the water will be always 99.6 degree. This is how we can easily define with the boiling point of the water, and it can be expressed in a two way, that is with the normal boiling point and also with the second one, the standard boiling point. Only when the pressure is equal to 1 atm, only when the pressure is equal to 1 bar. Next we'll see with the surface tension. The surface tension is a characteristics properties of the liquid. The surface tension is mainly because of the unbalanced force which is experienced by the molecules at the surface of the liquid. So it is nothing but the unbalanced force which is caused on the surface of the liquid. In the bulk of the liquid, each molecules, they attracted equally in all the direction and the neighboring molecules. Hence, these molecules do not experience a net force. On the surface of the liquid, we observe that if you take any bulk of the solution, what will happen? Almost all the particles or almost all the molecules, they attracted towards each other and they do not experience any net forces. However, the molecules at the surface do not have molecules on all the sides around them. Hence, they are pulled towards the liquid core by the non-zero net forces. Especially, at the surface, if you consider on the surface of the liquid, at this point, the molecules, it never attracted towards any other molecules in all the direction, and they're experienced by the net forces and they pull towards the liquid core. So for that, the liquid tends to minimize the surface area. A drop of the liquid tends to attain the spherical shape and become sphere and offers a small surface area for the definite volume, and energy is required to increase the surface area of that liquid in 1 unit are known as surface energy. Understand here? We have learned that. So the surface tension is nothing but a characteristics properties of the liquid, where we know that in the bulk of the solutions or in the bulk of the liquid, almost all the liquids or the particular molecules, they are attracted towards each other. Especially at the surface of the liquids, the particles are not attracted equally in all the directions. Hence, they are pulled towards the liquid core. And also they exhibit or they experience the non-zero net forces. As a result of this, what will happen? The liquids, they tends to minimize the surface area and the drop of liquids will be converted into spheres. They converted into spheres. Okay. As a result of this, what will happen? It will acquire certain volume and also it requires a certain amount of energy for it. That is said to be surface energy. The energy is required to increase the surface area of the liquid by 1 unit volume. By 1 volume, the surface area will be increased. For that, it requires certain energy. That is said to be surface energy and the unit is known as joule per meter square. The perpendicular force acting on the unit length of a surface of the liquid is known as surface tension. What is the surface tension? It is a perpendicular force which is acting on the unit length and the surface area of the liquid is said to be a surface tension and it is also denoted by gamma. That is, surface tension is equal to force divided by length. If the energy is required to create that 1 unit volume, what will happen? The energy per unit volume on the surface of the liquid will be also known as surface tension and it is also denoted as energy divided by area, where you are considering the force, where here you are considering the energy. The magnitude of the surface tension of a liquid depends on the attractive forces between the molecules. When the attraction forces are larger and surface tension will be decreases and the temperature will be increased. The surface tension is mainly depends upon the force of attraction between the molecule. When the force of attraction is more and more, what will happen to the surface tension? It will be decreased with the increasing in the temperature. For that, we have a unit in the SI system. We have a Newton per meter or joules per meter square. In CGS system, we used to represent in ergs per centimeter square. An example of this surface tension which we also observed in our daily life, that is drops of the water. When you are using the water dropper, the water does not flow in a continuous stream, rather in the series of the drops. The shapes of the drops is caused because of the surface tension of the water. So, you might have been seen in the chemistry lab where you are using the dropper to take out the solution, where if you use the dropper to take out any solutions or any liquids, the dropper will drop the water or any solution drop by drop. This is mainly because of the surface tension of that entire, entire pipe, or we can say it is a dropper along with the water. And also we can see the same thing in our daily life, especially the insects are walking on the water. The small insects such as the water spider can walk on the water because of their weight is not enough to penetrate the surface tension. Similarly, you would have seen with the spider, especially the water spider, these insects, they easily walk on the water because they don't have much weight to penetrate with the surface tension. We can also observe with the capillary actions of the water. The liquid tends to raise in the capillary because of the surface tension, and the surface tension pulls the neighboring water molecule along. So, you would have seen with the green plant where the water is sucked from the roots towards the all parts of the plant body where the capillary action is taking place. Here also the surface tension will work where the water molecules on the surface, it will create a bubble and it carries the water molecules to move along with that. Okay. So, in the next class again we are going to discuss with the viscosity and alumina flow. That is the last topic of this unit. And in addition to this, we are also going to do with some of the numericals. Okay. So, today whatever the things which have done in this session, it is also very important for the examination point of view, especially with the liquid, the surface tension along with the boiling point and the vapor pressure. When it comes to the gases, especially with the critical volume, critical temperature and critical pressure, it is also very important for the examination point of view. Hope you all understood and we will meet you in the next session. Till that, take care and be safe.